Alright, so the lines pi over 2 and negative pi over 2 are the horizontal asymptotes, whereas before, alright, those were our vertical asymptotes with the regular tangent function versus the tangent inverse function. Okay, and lastly, remember, this still all goes back to the domain of one is the range of the other when we're doing the inverse functions. Okay, so that's why the horizontal asymptotes are now going to oscillate between negative pi over 2 and pi over 2, and then the function is going to continuous on and have an infinite domain. Okay, so let's look at cotangent. Very similar to how inverse tangent was. So sorry, I meant to say inverse cotangent or arc cotangent. Very similar to arc tangent or inverse cotangent. The domain will be negative infinity to positive infinity. And remember, with cotangent, the domain was 0 to pi. That's where our asymptotes are. Now that's the range of arc cotangent or cotangent inverse. And remember how cotangent went from negative infinity to positive infinity, or positive infinity to negative infinity in the range. It's now the domain for the inverse function. Okay, so very similarly, to tangent, so I'm not going to step through this one too much. Secant, cosecant, they're going to be very similar. What we're really doing, though, is those cutoffs on the limits on the domain and range. Okay, so remember, on secant, right? Remember that's tied to cosine. So remember, if we graphed secant, all right, we had the parabolas up and the parabolas down, where we had to graph cosine first, and then it related to the graph of cosine. So when cosine had a maximum, secant had a minimum. All right, so remember that secant, the range went from -1 to infinity and negative infinity to -1. Now that's the domain. All right, so we've swapped the domain here. The domain is negative infinity to -1, and the domain is 1 to infinity. So notice that no values exist in the domain between -1 and 1. Okay, and then the normal range for secant, or for arc secant, is what the domain was for secant. Remember, the domain for secant, okay, was happening every pi because we had division by 0. Alright, so in this case, we're going to go 0 to pi for the range. So that's the limitations on the range. Then cosecant, remember that's tied to sine. So remember, cosecant is where we graphed the sine wave. Alright, and then we had a bunch of parabolas, so where sine had a maximum, cosecant had a minimum, and where sine had a minimum, cosecant had a maximum. So remember, the range on the regular secant function was negative infinity to -1, and then 1 to infinity. That becomes the domain of the cosecant function, inverse function, or the arc cosecant. So notice that's the domain, negative infinity to -1, and 1 to infinity. Then we had the range, or the domain on secant before. All right, that's the asymptotes. That's when sine went to 0. So that was at negative pi over 2, so on and so forth. Okay, so that's where we're swapping these out. The domain of one becomes the range of the other. So the limitation on cosecant inverse is negative pi over 2 to pi over 2. So really understanding all these is going to be the effect of, does your answer exist in the correct domain and range when we do some of these homework assignments. Okay, so here's a big chart. You guys can write this down and place this in your notes for something you can follow. So this will help you figure out if it's in, if one of the homework problems is asking you, is this a valid answer for like arc cosine or arc sine or arc secant? You can see it's got to fit into this specific interval for the range and the domain. All right, so the answers have to rely in the correct domain and lie in the correct range. And we can see where the quadrants of the unit circle, where we're going to have that happen. Okay, so this is a good chart to have in your notes as you kind of go through and do your homework problems. All right, so let's take another example here. So example 3, we want to find the degree measure of theta in the following. So theta equals arc tangent of 1. You can always check this in your calculator. Alright, so make sure that you're in radian mode because it's 1, and we can tell because it's not degrees. Okay, so what angle of theta gives us a tangent ratio of 1? That's really what we're looking for. Okay, so for us, theta has to be in negative 90 to 90. Since 1 is positive, theta has to be in the first quadrant for this one. Okay, if it was negative 1, we'd be in the other quadrant for theta. And you can go back and look on the charts. Okay, so we want to find the angle which that happens. Alright, using our triangles, we know we're looking for what? A 45, 45, 90 triangle, because we're looking for when theta creates a ratio of 1, and that happens with our 1, 1 square root of 2 triangle, because remember, tangent is opposite over adjacent, where it's 1 divided by 1. That only happens in a 45-degree angle. Okay, so either going to get pi over 4 in radians, or you're going to get 45 degrees in degrees. Sorry about that. Does that make sense? Okay, now let's find secant inverse of 2. You know, always ask yourself, is that 2 in that correct range for us? So yes. Okay, and then theta needs to be in quadrant 1 or 2. So since it's positive, we're going to roll with quadrant 1. Okay, so we have to find secant inverse of 2. So we need to think about what triangle is going to help us here and have a 2. Well, we have a 1 square root of 3, 2 triangle. Okay, so that's what you got to think about, because think of secant still in the form of cosine. Alright, so instead of adjacent over hypotenuse, it's hypotenuse over adjacent. So you're really thinking of, you know, a 1/2 versus 2 over 1. And with secant, it's 2 over 1. With cosine, it's 1/2. And the only one that fits for us is our 60-degree angle. So once again, remember in your notes when you're doing these problems, have your specific triangles out that we need to know the exact angles for. So have your 1, 1 square root of 2, 45, 45, 90 triangle. Have your 1 square root of 3, 2 triangle, which is your 30, 60, 90 triangle. When we're solving these, it'll really help you kind of understand and be able to look. Alright, so if you think about these, what I really want you to know and understand is you're finding what angle gives me the specific ratio. So if we just look back at, you know, what angle of theta gives me a tangent ratio of 1? That's really, you know, kind of how you have to see it. We're kind of working backwards. We're finding the angle. Okay? Alright, so let's do this one in radians here. We want to find y in radians. If y equals cosecant inverse of -3, so we put the calculator in radian mode. Remember, we can't do secant, cosecant, and cotangent. There's no buttons for them, so we have to make sure that we rewrite them in sine, cosine, or tangent forms to use a calculator. So in order to find radians of cosecant inverse of -3, we have to use the sine inverse function. So with your calculator, hit mode, make sure you're in radians for this one. Alright, so you do have to pay attention in this assignment whether it's asking for the answer in degrees or if it's asking for the answer in radians when you go through this. Alright, so in radian mode, you're going to hit sine inverse of -1/3, and you need to make sure that you put that 1/3 in parentheses to do this. So remember, when we're finding the angle with cosecant, you got to put it into sine. With secant, you're going to put it into cosine, and with cotangent, you got to put it into tangent. All right. So when we substitute this into our calculator, we end up getting -0.3398. You know, you got to remember this is in radians, so that answer does make sense. If we were looking for degrees and we got an answer like that, then it wouldn't make sense. Okay, but since it's in radians, that answer should make sense for you. Okay. So let's find degrees of arc cotangent of -0.3541. So remembering, in this particular example, we need to put our calculator in degrees, and we're given the ratio of 0.3541. That's not a nice, perfect 30, 60, 90 triangle or 45, 45, 90 triangle. So this one is strictly like a calculator type problem, or in the olden days, they used to have a long table that you would look at and get the approximation values, and that would tell you the answer too. Okay, All right, so remember, put in your calculator correctly. Okay, so when you do this, you have to pay attention to what quadrant that you're going to lie in. So we have to make sure that when we get in the right quadrant, okay, we have to make sure that we might have to add or subtract 180 to our answer. Okay, so when we do inverse cotangent of a negative number that's a quadrant 4 angle, okay, you got to remember it's a quadrant 4 angle because we're going clockwise right away, not counterclockwise because it's negative. Okay, the restrictions on the range for us, so this is going back to your table, is saying that we have to be in quadrant 2. So when we do something like this and we have a negative angle, all right, it's very imperative that you have that domain and range chart out so that you know when you have to add 180 and when you don't. So when we do this, we're going to do tangent inverse of 1 over negative 0.3541. Remember, that's because we don't have cotangent in our calculator. So arc cotangent or cotangent inverse, we have to do 1 over in the argument piece for that. So that's what we're doing, tangent of inverse of 1 divided by negative 0.3541, and then we have to add 180 to that so that we end up in the correct quadrant for the domain and range values. Okay? So when you do that, enter it into your calculator as such. Tangent inverse, okay, of 1 divided by negative 0.3541, making sure that we're keeping parentheses. If you don't put the argument in parentheses, you're going to get the wrong value. So you got to really remember to do that. All right, and then plus 180, so that puts us in the correct quadrant when we go through there. All right, so you should approximately get theta to be 109.5 degrees when you go through. Okay, so these are just the cautions. When you do inverse cotangent of a negative quantity, make sure that you are ending up in the correct quadrant. Note that the wrong answer will be an answer choice on your homework assignment and on a test. So make sure that you're doing your due diligence of checking that out. Okay, making sure that you know that you're in the right quadrant when you do this. Okay, and down at the bottom, instead of the question mark, it should say pi, because if we're in degrees, we're adding 180. If we are in radians, we are adding pi to the answer because it's giving us a 4th quadrant answer and we need a 2nd quadrant answer. Okay? Alright, so let's try and do some of these without a calculator. Alright, without a calculator. So what's going on here? We kind of have like a composite function. Remember, like f of g of x or g of f of x that you learned in algebra? So we got kind of a composite function here. We have sine of tangent inverse of 3 over 2. All right, sine of tangent inverse of 3 over 2. So that tangent inverse of 3 over 2, that's a specific angle, okay, and that's the entire argument for sine here, okay? So we got to find, some different ways to evaluate this. So we're going to say theta is tangent inverse of 3 over 2. Okay, so when we write this out, we know that we can say that tangent of theta is 3 over 2. That's how we're undoing the arc tangent, okay, or the tangent inverse. So remember I said, when you're looking for an arc cosine, an arc sine, an arc tangent, an arc cotangent, secant inverse, cosecant inverse, what you're really doing is looking for the angle. So what this really tells me is tangent of theta is 3 over 2. That's important for us because now we can draw a triangle, because we know tangent's opposite over adjacent. We're able to now find the hypotenuse of that triangle. Once we know the hypotenuse of that triangle, then we can find what the sine value of that is, okay? So very, very important. So we can only make sure this is only defined in quadrants 1 and quadrants 4, all right? So when we do this, we're going to choose the quadrant 1 angle because it's the positive angle. All right, so we're going to sketch the triangle and label it. All right, so when we find the hypotenuse of that triangle, it ends up being square root of 13. Right, we got 4 squared, or 2 squared plus 3 squared. So we got 4 plus 9 square root of 13, and that's going to stay prime like that. So what we want to do is, we know that tangent inverse of 3 over 2 is going to be what? Tangent opposite over adjacent, so that's 3 over 2. That helps us rewrite the sign. Sine in this case is now going to be opposite over hypotenuse, which is 3 over square root of 13. And then we have to rationalize the denominator, so we get 3 square root of 13 divided by 13. Okay? So hopefully that helps make sense. That's our theta for that. Alright, let's do another one. We got tangent of cosine inverse of negative 5 over 13. Same procedure here. Okay, same procedure. We know that cosine of theta is going to equal negative 5/13. Alright, so that tells us that we are able to draw our triangle out. So once we draw our triangle out, this tells us what? That we are adjacent over hypotenuse. So it's going to be negative 5 over 13. Alright, and then we're going to have to draw the triangle. And we're going to pay attention to cosine's negative. Okay, so arc cosine is defined only in quadrants 1 and 2. Since it's negative, we have to choose the quadrant 2 angle. Okay, remember this is a little different than the all students take calculus, because we're talking about the definition of the inverse functions, not the regular sine, cosine, tangent functions. Okay, so that's why it's only defined in those specific quadrants. So that's why that chart that I showed you before comes in really handy. Okay, all right, so we're going to sketch a quadrant 2, okay, when we do this triangle. So we have negative 5, 13, so we got to go 13 squared minus negative 5 squared. Okay, so we got 169 minus 25 is 144. Square root of 144 is 12. Okay, so now we can rewrite this as tangent of cosine inverse of negative 5 over 13. That is equal to tangent of A. Okay, and we know that tangent of A is what? Now tangent's opposite over adjacent, so that it ends up being negative or a positive 12 divided by negative 5, which is negative 12/5. Okay, so we're using one function to work through and find the other function. Alright, so we're going to evaluate this expression without a calculator. So we have cosine, and then the cosine of the angle, okay, the argument here, is arctangent of square root of 3 plus arcsine of 1/3. Okay, remember you can write that as tangent inverse of square root of 3 plus sine inverse of 1/3. However you want that to work out. Okay, so we have a couple of angles here that we have to sum. So we're going to start pulling all kinds of stuff from our previous chapters in here. So we are going to say that angle A, okay, is the arctangent of square root of 3, and angle B is the arcsine of 1/3. So now we have what? Cosine of A plus B. We have a cosine sum identity that we're going to have to work through to help get this problem out. What else are we going to have to find? We're going to have to find the other values of the triangles that are missing. You know, this is all prior knowledge now, finding the different values. Okay, so we know that A is square root of 3, B is 1/3. So we might have to find what? Sine and cosine of A. We might have to find cosine and tangent of B. Since we're given part of it, we're able to find those other missing angles. Okay, so we're going to sketch them out, and we're going to use the Pythagorean to find the missing pieces. Okay, so we know sine of A is square root of 3 over 2, and cosine of A is going to be 1/2. That's because we were given what tangent of A was, right? Tangent of A was square root of 3, which really meant square root of 3 over 1, right? Because tangent of A is opposite over adjacent. So we are able to draw the triangle here on the left and find the sine and cosine component for angle A. Then over here on the right hand side, we were given what B was, right? So given what B was, we're able to find the other ratios. So sine of B is going to be 1/3, cosine of B is 2 square roots of 2 divided by 3. Okay? Because we were given what? Of one, or sine of B was 1/3, so that was our opposite over hypotenuse, right? So we knew the hypotenuse was 3, the opposite leg was 1, so we had to use the Pythagorean identity. So we did 3 squared minus 1 squared. Okay, that gave us square root of 8. okay, for that leg, and then square root of 8 breaks into square root of 4 times square root of 2, which breaks us into the 2 square roots of 2. So that's the adjacent side. So we have 2 square roots of 2 divided by the hypotenuse, which was 3. And if we needed tangent of b, right, tangent of b would be opposite 1, right, divided by 2 over the square root of 2. We'd have to rationalize that denominator in the bottom. All right, so we'd have square root of 2 over 4. Okay, so we have to use the sum identity because there's two angles being added to each other. So remember, the cosine sum identity is cosine A cosine B minus sine A sine B. And now we evaluated the functions, so we know that we know the values of A and B for sine and cosine. We substitute this in. So this is all prior knowledge. This is, for us, pretty much doing what we've been doing in the last chapter over and over again. Okay, so we end up getting 2 square roots of 2 minus 3 over square root of 6. Okay, but what does that really relate to, and what's the point of this problem? I'm going to step back a couple slides. You had to understand that we had to find our theta and set up our triangle using the arc tangent of square root of 3 and the arc sine of 1/3. All right, that's really what you had to do, is be okay, that means that angle, and I'm given the ratio, and you had to use that ratio to find these missing pieces to plug into this cosine sum identity. All right, so let's do another one here. Without a calculator. So we have tangent times a quantity, or tangent with a quantity, not times a quantity, but the quantity of 2 sine inverse of 2/5, or 2 arc sine of 2/5. All right, so we got that 2 in front that's kind of throwing us off here as we do this problem, but we do have, sine of theta has to equal 2/5, all right, and then there's a 2 in front of that. So we have to really be careful. We only have one angle here in question. We have B, so we're going to say that B is arc sine of 2/5, so sine of B is 2/5. Okay, so this is our double angle identity on this piece, so this is where we're really pulling that chapter 5 stuff in. Okay, how do we know it's a double angle? We got that 2 in front. Okay, so we have to rewrite this. All right, we're going to write tangent of 2b equals 2 tangent of b over 1 minus tangent squared of b. Well, we have the sine, so we have to find the tangent pieces, or we could find the cosine piece as well and use tangent as sine over cosine when we do this. Okay, so you have to recognize the double angle identity, and to recognize that, that's because the 2 is in front of the arc sine. So it really looks like tangent of A, right, on your trig identity sheet, or sorry, tangent of 2A on your identity sheet, where A is the arc sine of 2/5. Okay, that's the angle. So remember, the arc sine and the inverse, that means the angle piece on that. So really identifying that, and then the rest, we just use the Pythagorean, draw the triangle that you're given. Okay, so we're given the sine piece, so we're given the 2/5. So we need to find the tangent of that angle, so we have to use the Pythagorean. So it's going to be 5 squared minus 2 squared, so 25 minus 4, all right, is 21, so it's going to be the square root of 21. Tangent is opposite over adjacent, so it's 2 divided by the square root of 21. Rationalizing the denominator, we end up with 2 square roots of 21 divided by 21. All right, so that's our tangent of B, and we're going to substitute that in here into the double angle identity. Please remember, when we substitute in, some people in class, I know you've been making errors, when we substitute in tangent of B, the word tangent goes away. We replace all of tangent with that function, okay, or with the actual ratio that's remaining. So this becomes 2 times 2 square roots of 21 over 21 divided by 1 minus 2 square roots of 21 over 21 squared. Make sure when you take that quantity and square it, you square the whole thing. You square each term. So I'm talking about in the denominator there, the 2 gets squared, the square root of 21 gets squared, and 21 gets squared. So 2 squared is 4, square root of 21 squared is 21, and then we have to square root 21 there. Now, you don't necessarily have to do that if we're going to multiply through and clear out the denominators, but from here, it's pretty much algebra that you should be able to kind of pick up and go through. So work through it. Let me know if you email me if you need me to fill in some of the gaps on the algebra. All right, but this is 4 square roots of 21 divided by 17. All right, let's do it in terms of u now. This is more going to be some good intro to calculus sort of thing for us as we write it this way. Because not everything's going to have angles, and we want to be able to do our calculations for anything that we can substitute in. So this is a good one, a good segue. We're going to be in calculus soon, next semester, and a good segue in for this. So we're going to write sine of the quantity of tangent inverse is u. And now we're not going to get a specific value. Everything we're going to write out is going to be in terms of u. Okay, so we need to understand that theta, all right, because we want sine of theta. So theta is going to be tangent inverse of u, so that we can say that tangent of theta is u. That's very important for us. We have to write that first step. So remember, we're solving for tangent of theta equals u based on the restrictions we have on theta. Now that we can rewrite that, okay, all we're doing is rewriting the function. So this is like we did at the beginning of the chapter, where we swap x and y and then resolve for y. It's kind of the same concept there. All right, we should be able to rewrite our inverses into the original functions. So tangent of theta equals u. That's important. It's really u over 1. So this allows us to draw our triangle. Okay, so the opposite side is u. The adjacent side is a 1, and then based on that we can use the Pythagorean identity to find the hypotenuse of the triangle. Okay, so we have to make sure that we understand u can be positive or negative here, and we need to know that the restrictions on theta based on it being arctangent have to be in quadrants 1 and 4. So where does that square root of u squared plus 1? Well, since we're given u, and I just explained that, right, tangent of theta equals u, u is opposite over adjacent, or theta is opposite over adjacent, so it's u over 1. And then we have to do the Pythagorean, so u squared plus 1 squared, all square rooted, gives us the hypotenuse. So that's where that's developed from. So we have these two possible solutions here, right? One's in the first quadrant, one is in the fourth quadrant. And remember that this is all going to be in terms of u, so we have to find sine. So this is very, very important, because this is how we treat this in calculus as well. When we do derivatives and things like that. So this is an important concept that you really need to understand, is writing all these functions in terms of u. All right, you might see a lot more of these on your test. Just a hint there, okay? So, very important. So when we write sine of theta here, sine of theta is opposite over hypotenuse. So sine of theta is going to equal u over the square root of u squared plus 1. Now we have to rationalize the denominator in this case. So we're going to multiply the numerator and the denominator by the square root of u squared plus 1. So when we do that, rationalizing the denominator, we get u times the square root of u squared plus 1 divided by u squared plus 1. I really want you to take your time on these problems and do these well, because you will see these in the future. Okay? Let's do this one. We want to write cosine of 2 sine inverse of u as an algebraic expression of u. Well, what should that tell me? I see that 2 in front of the sine. I should automatically be looking at my trig identities, being like, oh, it looks like I got a cosine of 2a. So I've got a double angle identity that I need to apply here. Okay? But first and foremost, we got to put sine in terms of u. All right, so theta is going to be sine inverse of u, so sine of theta is equal to u. So now remember, sine is opposite over hypotenuse. So it's really, sine of theta is really u over 1 there. All right, then we have to find that adjacent side. So it's going to be 1 squared minus u squared, all square rooted when we do that. But for us, okay, since we have sine, we got to make sure we choose the right double angle identity. So cosine of 2 theta is 1 minus 2 sine squared theta. All right, and we're going to substitute all that in. Okay, we can do it this alternative way. Since we know cosine of 2 sine inverse of u is equal to 2 theta 1 minus 2 sine squared theta, we can rewrite that as 1 minus 2 u squared. I probably just lost everybody on this one. Okay, so let's back up a couple steps. So on the previous problem, and what I started to talk to you about on this problem, is how we could go through, draw the triangle, and solve everything out and plug in. This is where the double angle identity makes it easier for us, because we know, if we look at the original problem, it's 2 sine inverse of u, right? That's 2a, essentially. Looking at your trig identity, we can rewrite cosine of 2a as 1 minus 2 sine squared of theta. Everybody's on board there. Now, since we know that theta is sine inverse of u and sine of theta is u, we can literally substitute in u where sine of theta is in the identity. So we can rewrite this as 1 minus 2 sine squared of theta, and wherever there's a sine squared, we replace it with u. So we're going to get 1 minus 2u squared. Okay, so that's the alternative method. So there's 2 ways of doing it. The first way where I explained through, and you can do the triangle, find the missing pieces there and substitute in, or use the double angle identity and do it this way as well. Okay, so let's take a look at a real world type problem with this. Of elevation theta that a shot putter, alright, so this is, we're talking like a track event here. Shot put's a little metal ball. There's 12 pound, 13 pound kind of balls that you're going to, traject for a certain distance. It's a competition if you don't know what shot put is, okay? Shot putter should aim in order to throw the greatest distance, and it depends on the velocity of the throw and the initial height of the shot. Alright, so you want to get enough height and you want to release from a specific position, alright, so that you can get maximum distance. Alright, so we got to think about some different things here, right? We have the angle of elevation, okay, what we're going to, to the trajectory we're putting it on, how fast, our arm can come forward and traject the ball, and the velocity, right, and how high we're shooting it from. Okay, so you have a bigger advantage if you are a taller person than a shorter person for this. So a way to model this, okay, obviously using inverse sine, because we want to be able to find the optimal angle for us, okay? So one model for theta that achieves this, okay, is sine inverse of the quantity of the square root of v squared divided by 2v squared plus 64h. Okay, so if we have a shot putter who can consistently throw the ball, okay, with a height of 6.6 feet and a velocity of 42 feet per second, at what angle should he release the ball to maximize distance? Well, we're given height, we're given velocity. Your first instinct should be to do what? Hopefully you said substitute those values in. That would be a great idea. Okay? Substitute those values in, and then on your calculator, make sure you're in degree mode, and you're going to do sine inverse of whatever that entire radical works down to. So you have 42 squared. Keeping track of parentheses. When you get to a problem like this, I would do it all in parts in your calculator and get a value that you want to take arcsine of. I would not try to type this whole problem in the calculator unless your calculator is really good at defining orders of operation and things like that. But in your calculator, you can substitute this in, and you'll get 42 degrees back. Chapter 1, my apologies, it came in 3 parts. My video capture software kind of conked out on me a couple times as we were going through this. But, you really need to take your time in this chapter, work through problems in this section. Step back, look at the problems on the homework, and then come back and look at the examples. And you need to be able to go back and forth. Make sure that you take really good notes. A lot of the homework problems are just like the example problems, but you need to kind of think through some of the steps, be able to work through them. This section is a little bit challenging, but once you get the hang of it, once you get the hang of doing this inverse rewriting back and forth, I don't think that you're going to have any problems with it. But the first 5-10 problems you're going to struggle with, and then as you move through the assignment, all right, you'll be doing good, and then we're going to get to the U stuff, and you're going to get confused again, but do it the same way. All right, go back, look at the examples. You guys will be fine on this, but this is an assignment that you need to take your time on. Try not to fly through it. Make sure you give yourself plenty of time to work on it. This isn't going to be knocked out in an hour type of assignment. All right, so as usual, email me if you got questions or need problems worked out. Else I'll see you guys in class.